in which he made important fundamental contributions. But in studies of the stars, the call is always, in his own words, for more light, which means larger and larger telescopes. Hale persuaded friendly millionaires to finance his plans. On Mount Wilson, outside Los Angeles, there rose a 60-inch reflector. That was in 1908. But already, Hale was planning a 100-inch reflector, and in 1917, his dream was realized. That was the Hooker reflector, so named because that particular millionaire's name was Hooker. Using the 100-inch, Edwin Hubble, later to become one of America's greatest astronomers, was able to show that the so-called starry nebulae are in fact independent galaxies far beyond our own. And yet, Hale wasn't satisfied. A 100-inch mirror? Why not a 200-inch? It sounded like another wild dream, but Hale persevered. First, the site. The original choice for the 100-inch Hooker reflector had not been Mount Wilson, but Palomar. Palomar, though, was less accessible, and before the First World War, that mattered. By the time the 200-inch was planned, transport was easier, and so Palomar, further away from the lights of the growing city of Los Angeles, was chosen. Obviously, the initial stages were to work out the form of the mounting, the design of the dome, and above all, to make the mirror. No mirror, no telescope, and casting a 200-inch glass disc is not easy. Quartz was tried, but reluctantly abandoned after a lot of testing. Pyrex was then chosen, and after a good many trials and tribulations, the mirror was cast. It took months to cool, and then it had to be carefully ground to the correct curve. In 1938, Hale died. It's sad that he didn't live to see the telescope completed, but at least it's good to know that he realized it would be completed. Then came the war, and that meant a halt. After the war, work recommenced. The chief designer was the Vermont architect Russell W. Porter, whose technical and highly accurate and artistic drawings of the dome, the buildings, and the telescope itself were of great value in working out the final design details. At last, the mirror was finished. Then it had to be taken to its site on the mountain. A special road had been built, but it was an agonizing journey. It arrived at the mountain at the beginning of a freak storm. Had it been delayed, the vehicle would have had to cope with treacherous sleet on the road. It was a great relief for everyone when the trip was safely over. The inauguration ceremony, 1948. 300 people there. The main absentee was, of course, George Hale. There's one point that I always find interesting. The mirror's coated with a thin layer of aluminium, and by thin, I mean thin, the tiniest fraction of a millimeter. It's this aluminium film which collects the light from the object you're observing, and so the whole telescope, with its 500-ton mass and its 1,000-ton dome, exists merely to move this flimsy aluminium layer around. Movement has to be perfect. The telescope can be preset to an accuracy of 1/10 of a second of arc. And of course, it's guided automatically to allow for the Earth's rotation on its axis. Yet everything is so perfectly balanced that the motor used for turning the telescope generates only about half a horsepower. The horseshoe turns on a very thin layer of oil, pumped in at high pressure. The layer's only 3/1000 of an inch thick. Why was the telescope built? Well, from the outset, the telescope was designed to study objects a very long way away from us. You just don't use a 200-inch telescope to look at the moon and planets. Although in the very early days, even before the final adjustments were made, some lunar and planetary pictures were taken. And some of those, such as the picture of the crater Copernicus on the moon and the red spot on Jupiter, have been reproduced time and time again. But that wasn't the purpose of the 200-inch. Its role lay among the stars and galaxies. Periodically, the mirror has to be taken out of its cell to renew the aluminium coating. But it's a tricky process. Remember, it's large and massive. When the mounting was being tested, a concrete block was put into the tube to simulate the mirror, and this is it. Looks impressive even when lying here. And do look at that hole in the middle. That's because one way in which the telescope can be used is as what's called a Cassegrain. The light from whatever you're observing strikes the main mirror and is reflected up the tube onto a smaller curved mirror, which sends the light back to focus through a hole in the 200-inch itself, this hole in fact. It's only one of 3 optical systems which can be used, but it's an important one. When the dome moves, I think you can really appreciate its actual size. I certainly don't know of any dome that's more impressive. And here is the mirror, the heart of the telescope, accurate to within a tiny fraction of a millimeter. For a long time, the observer stationed himself in a cage actually inside the telescope tube. The mirror may look flat, but it's not. It's curved. What happens is that the light from whatever you're observing comes down the skeleton tube, hits the mirror, and is reflected back here onto what we call the prime focus. So there's no flat mirror, as there is with the more conventional Newtonian system. And so this is where you put your photographic plate. I need hardly say that you have to take great care not to drop anything, because even a penny falling from this height onto the mirror would do a great deal of damage. And before coming up here, I even took the precaution of removing the reading spectacles from the pocket of my jacket where I usually carry them. Normally, after a night's work, the observer would end by coming down on the platform, but times have changed, and the 200-inch has shown its ability to change with them.
When this telescope was first built, the observer used to sit at one of the foci looking at an eyepiece, and in the cold usually, and the assistant who ran the telescope would sit at a desk on the floor, also very often in the very cold. And now, with the advent of modern electronics, it's better for the observer and for the assistant to get out off the floor and out of the dome and sit in a control room. With the modern television that we have and new computers, you can do things much more efficiently because you have all your papers with you. In the old days, the telescope was run by ordinary motors that you would have in an electric clock. Now you have a computer that runs things like you do in modern quartz clocks. The thing is very accurate. The motors are servo-driven. The computers can calculate all the corrections of air mass and flexure of the telescope, so you can point to objects that are so faint you couldn't see them in an eyepiece in years gone by. But with the present TV cameras and modern electronics, you can integrate for a long time. In other words, look at the object for a tremendously long time compared to what your eye can see, and look further into the universe than you could ever do before.
Have there been any really major modifications to the telescope since it was brought into use in 1948?
The only real change is the control system, which helps the telescope perform much better. It's a very well-designed telescope, and it tracks very well. And with the advent of modern computers, it tracks even better.
And, of course, it can adapt to the modern electronic techniques.
Oh, definitely. Right now, very few people use photographic plates on it. It's almost all electronics. There are electronic sensors in the infrared where you can't see anything with your eye. There are electronic sensors like CCDs that can take pictures much fainter than photographic plates. There are sensors that take spectra with much greater accuracy than photographic plates and much faster. All in all, it's improved. The telescope has advanced with advancing times, even though the mechanical structure is old.
I think most people are familiar with the magnificent star pictures taken with the 200-inch over the past 30 years. They range from the beauty of the gaseous Orion Nebula, to the fascinating Ring Nebula of Lara, to the starry Andromeda Spiral, and to the faint blurs of light, which we now know to be independent galaxies, each containing something like 100,000 million suns. And yet these are very much more than pretty pictures, and in 1953 they led on to a discovery of immense importance. Most of the galaxies contain variable stars of the kind known as Cepheids. They change in brilliancy from one night to the next, and they're regular in behavior. Using the 100-inch on Mount Wilson in the 1920s, Edwin Hubble had studied these Cepheids. It was known that the way in which a Cepheid behaves gives a clue to its real luminosity and hence to its distance. Hubble found that the Cepheids in the so-called spiral nebulae were so far away that they couldn't possibly be members of our own Milky Way system. And that's how it was first found that there are millions upon millions of galaxies. Using the 200-inch with this extra light grasp, the late Walter Baade made another spectacular discovery. There had been an error in the Cepheid scale, and the result was that the galaxies were much further away than had been thought. Thus, instead of being a mere 750,000 light years from us, the Andromeda spiral lies at a distance of more than 2 million light years. Although even so, it's still one of the very closest of the outer galaxies. Without the extra light grasp of the 200-inch, that discovery wouldn't have been possible. And yet, the work of the 200-inch doesn't consist of taking spectacular photographs. Astronomically, the spectroscope has always been regarded as being of prime importance. Now, a spectroscope splits up light, and as it does so, it weakens it. Therefore, if you're going to photograph a spectrum of a very faint object, you need all the light you can get. The 200-inch is, above all, versatile, and it can make use of a third optical system, the coude. The main feature of the coude system is that the focal length is effectively increased, in this case to 500 feet. By using 2 extra mirrors inside the telescope itself, the light from the object under study is made to come out at a fixed position. It goes down to what's called the collimator to line the rays up with the grating, and then is reflected onto the grating where the actual spectrum is produced. The light then comes down to what's called the camera, actually it's a mirror, and then onto the photographic plate, which is here. Nowadays, of course, it will probably be an electronic device rather than an old-fashioned plate. Nothing in this coude room has to move very much, and that means you can make your equipment as heavy as you like, which you certainly couldn't do if you had to take it with you in the observer's cage. But we've got to remember that visible light is only a very small part of the total range of wavelengths, and the 200-inch is very well suited to observations in the infrared. Obviously, the telescope was designed for night use, but it can also be used in the daytime for specialized investigations. Infrared radiations, longer than those of visible light, can be collected and studied with the Palomar reflector. Dr. Eric Persson has been concentrating on this work, and he's in the middle of an observing run now.
We're measuring galaxies that are moving away from us at speeds around 100,000 kilometers a second and on up. And these are the most distant galaxies known and have only been discovered in the last couple of years. What we're trying to do is match up the infrared radiation from these objects with their visual radiation. We have some evidence that galaxies aren't the same as the ones that are nearby. Remember that for the most distant objects, we're looking back 5 billion years or so.
When you're studying very faint, very remote objects, the tremendous light grasp of the 200-inch must be a great advantage.
One can't really do this kind of work with telescopes too much smaller than the 200-inch. We also have advantages in being able to take a picture with a television camera of the fields that we're measuring, the galaxies that we're measuring, and we can set on them very accurately and sit and measure away for a couple of hours, maybe 4 hours at a time.
The 200-inch itself is more than 30 years old now, but it's fair to say, isn't it, that you're using it to advantage with the most modern type equipment.
That's right. The infrared technology we have now did not exist 5 years ago, and we could not have made the measurements at all 5 years ago. They're just barely possible now, and in 2 years perhaps we'll have more signal to noise, and we'll be able to reach fainter and fainter galaxies as they're discovered.
But there are problems too. We all know about the increased amount of scattered light in the sky due to artificial sources. The growth of Los Angeles has already had serious effects on Mount Wilson Observatory. Palomar's further out, but can it escape the continued growth of city lights and pollution? Obviously, one man, above all, to whom this is of paramount importance, is the director of the observatory, Dr. Gary Neugebauer. His special research is in the infrared, but atmospheric pollution is evident there too, as Dr. Neugebauer stressed when I asked him about it in Pasadena.
Palomar is located right in the center of the fastest growing region of California, and the lights are encroaching more and more on the sky.
When Palomar was originally built, it was thought to be far enough away from Los Angeles for the lights not to matter.
That's true, but nobody thought of San Diego in those days. This is a picture of the coast of America taken from a satellite, and in this picture, it was taken at night, the lights show up as black. And so what you're seeing here is the coast. Up here is Washington and Oregon. Down here is California. And the black are the lights from the cities and the towns. Down here is Los Angeles. Right below it is San Diego. And Palomar is sitting right in this little niche right in here.
So you can see that the lights from both Los Angeles and San Diego are slowly encroaching on where Palomar is located. So we're still safe for a little while, but after a while we just see the lights from both places growing in to cover up Palomar. So we have to work very hard now to make those lights be sensible so that we can save Palomar. We want to change the light to be restricted to narrow wavelengths so that we can filter it out. Also, of course, we want to make all the lights be pointing down instead of be pointing up into the sky. And there still are many nights when there's fog, and so the cities are blanked out, and those nights, of course, are the good nights. But with the eventual growth of that area, that's what we're worried about, and that's why we have to do something now to save it for the next 20 years. But right now, we're still gaining, and we're still doing much better than we were doing in Hale's day.
Originally, the astronomer had to depend upon his eyes alone. Then, in the 19th century, photography was developed, and by Hale's time, the photographic plate had replaced the eye for most branches of astronomy. In our own century, there's been another revolution in optical astronomy. Photography itself is being superseded by electronic devices. Remember that when Hale planned the 200-inch, he knew nothing about such techniques. They lay in the future.
Taking over now are instruments such as the CCD, or charge-coupled device.
With this CCD detector, we can see 10 times further into space than previously with the 200-inch. We've been working on 3 main projects. The first is we've looked at galactic nuclei of nearby very strong radio galaxies. They may well contain very large, massive black holes, each of which is 1 billion times the mass of the Sun. This black hole eats the stars in the galaxy, and as it eats the stars, it generates a tremendous amount of radio noise, which is the reason why we see the galaxies in the radio. This mechanism probably also explains quasars. A second line of research we have done consists of looking at extremely faint and distant galaxies right at the edge of the universe. We can see galaxies out to a redshift of 2, which means we can see galaxies as they were 9 billion years ago. We can watch galaxies form. We can see how galaxies evolve during the time of the universe from then till now. A third line of research we have done with the CCD involves gravitational lenses. What we see in the gravitational lens is verification of Einstein's theory of relativity on a cosmic scale. Einstein's theory predicts that masses bend light in the same way that they bend particle trajectories going near them. What happens is that there is a quasar on the other side of the universe. The light rays from the quasar come towards the Earth, but pass near a galaxy which by chance is near the line of sight. The light rays pass on each side of the galaxy, and you see 2 images of the quasar instead of only 1. And sometimes you see 3 or 5 images of the quasar as the paths of the light find different paths around the galaxy. And using this effect and the simple geometry of triangles, we can actually measure the radius of the universe.
So the 200-inch is still very much in the forefront of research.
The 200-inch telescope is the most suitable instrument for my type of work, firstly because of its very large collecting area, secondly because of the extremely fine seeing we have at Palomar, and thirdly because we have a very well developed system of electronic CCD detectors which we use on it.
What exactly is a CCD?
It's a small wafer of silicon, 4/1000ths of an inch thick. It has 500,000 independent little picture elements embedded within it, each of which individually detects incoming light. The light which hits the CCD is converted into a tiny electrical charge and stored in the CCD. When we finish taking the picture, we use an electronic box to read out the CCD, to measure the amount of charge in each of these 500,000 picture elements, and we convert it into a number which we store in a computer.
How much does it cost?
This is only $500,000. The reason why they're so expensive is because we have a very high failure rate in making them. We make 100 and only a single one works. These have only come into being in the past 2 years, and the amount of information we can get from them is enormous. We can learn about the nature of the very early universe. I think that is the most important role for the 200-inch telescope in the future.
I think it's clear that whatever happens in the future in astronomy, whatever observatories are built, either in space or on the ground, that they are going to build on what has been accomplished by the 200-inch in the last 30 years.
All in all, I think it's safe to say that Palomar will remain the most famous observatory in the world. From here, astronomers have studied stars and star systems so remote that the light, now coming down the tube onto the great mirror, started its journey not only before humanity began, but before the Earth itself was born. And one thing is certain: there has never been a telescope that has told men so much in so short a time.